Okay, here we are with our second video on the binomial distributions. Here we're going to be talking about how to use the graphing calculator to help us out finding these probabilities. Whereas in the first video we talked about what a binomial distribution was and how to find the probabilities based on using the formula. Okay. Now, quick disclaimer there: using the formulas is the preferred method. However, if you're dealing with a problem that is in the multiple choice section, by all means, go ahead and use the calculator for it. But for the free response, the AP as well as I am looking for you to be using the formula to help you find those probabilities. But if we were going to be looking at a problem like this here, which is again our switch problem, where we have an SRS of 10 switches, we have 10,000 as our population, and we know that 10% of them are bad. Well, the calculator can calculate the probability of each individual value of x, meaning however many successes we're talking about, using the following command. And it says here, binom PDF. You enter in 3 values there. You enter in the n, which is the number of observations. We have the p, which is the probability of success, and the x, meaning the number of successes that you are looking for. Now, first you want to be able to find this command, binom PDF, and on your calculator, it is in the second vars menu. You have to scroll down a little while in that menu, but it is there. And then you need to figure out, well, how am I going to enter these in? Well, if you have the updated operating system, the calculator will prompt you for the number of trials or observations. That means the same thing. It will prompt you for the probability of success and the number of successes that you're looking at. All right? So if we wanted to do that for this particular example, we could look at this example here. It says, what's the probability that at most one fails? What do you think about that phrase, at most? That means you could have none of them fail, or you could have one of them fail. And all we have to do now is go ahead and plug in everything we need for this problem. So we go to our binom PDF. Okay, binom PDF is the function we're going to be using there. We have 10 switches that we are selecting. We have a probability of success of 0.1, and at first, we'll find the probability that none of them fail, and then we'll come in and find the probability that just one of them fail. We go ahead and hit enter on that, and we'll see it's 0.3487 for 0, and 0.374 for one of them failing, and we get an overall probability of 0.7361 of having 0 or 1 fail. Now, if you notice, when you found your probability distribution, or the binom PDF here, what you saw there was not just a binom PDF, but a binom CDF. Well, the PDF stands for probability distribution function. And we use this one when we're looking for getting exactly X successes. And in just a little while, we'll talk about when to use the CDF, but basically, the C stands for cumulative, so that would be if we were looking for, say, 5 or fewer successes, or 10 or more successes in a particular case, where we're looking for quite a big range of number of successes there. That would make using the binom PDF command or the formula much too cumbersome. All right. Now, let's look at it in another example here. It says, Corinne makes 75% of her free throws over the course of a season. In a key game, she shoots 12. Okay, so she shoots 12 and she makes 75% generally, and she only makes 7 of them. The fans think she failed because she's nervous. Is it unusual for Corinne to perform this poorly? And we're going to go ahead and assume that it's independent here. Well, whether it is or not, well, that's up for another debate, but not a debate that we're going to be having right now. So we want to answer this question here, and we're going to go ahead and say, well, let's think about that for a second. If she only makes 12, if she takes 12 and only makes 7, we are looking for the probability that she makes exactly 7. So, whereas we could come in with the formula, and we could say, she's shooting 12, how many different ways can you find 7 successes? And then we come in and say, okay, well, 0.75 is the probability of success. Raise that to the 7th power. And if 0.25 is the probability of success, then 0.25 is the probability of failure. And if she makes 7, well, that means she misses 5. We could go ahead and use the formula. And like I said, for the problems that are open-ended, that's what we are expecting of you. But since this is the calculator section, let's go ahead and do that method as well. we're looking for exactly 7 successes, so I'm going to come in with a binomial PDF command, and I'm going to show it using the older operating system, just because that'll make it so that everyone understands what's going on. Our n, which is the number of observations here that we have, is 12. Our p, which is our probability of success, is 0.75, and our x, meaning the number of successes that we're talking about here, is 7. And whether you use the calculator or the method that we used, that we showed here at the beginning with the formula, you end up getting 0.1032. Now, if we look at that, what does that mean? Because that's a pretty important understanding. That means that she's going to make exactly 7 out of 12, 10% of the time, 10.32% of the time specifically. So does that mean that she choked? Was she nervous? Well, no, because if something happens 10% of the time, then it's going to happen every once in a while. It could just as easily have happened by chance as any other reason that you might place there. Okay? So people say it all the time in sports, well, maybe he missed that throw, or he didn't get a hit, or whatever the case might be. That doesn't mean necessarily that they choked or that they failed because they were nervous. It just means that every once in a while things like that happen, and it just happened, unfortunately, to happen to them in a big spot. Okay? So that's an example of a binomial PDF. Let's look at the second question here and see if it is also something we can model using a binomial distribution. Second question here says, what's the probability of making her first basket within the first 7 free throws? Well, that means that she could have made the first free throw, and then that would have satisfied it, or she may have missed the first and then made the second, missed the first 2 and made the third, etc. You can imagine that's going to take us a while to figure that out, okay? But if we look at our hint here, it says find the complement. Well, what does that mean? Okay, what's the opposite or the complement of making her first free throw within the first 7 free throws? Well, what that means is that the complement would be all 7 were misses. So we can find the probability of all 7 misses. In other words, probability that x equals 0. And if we take that away from 1, that'll give us the probability that she makes her first free throw within the first 7. Okay? So all that means is we have to come in and do 1 minus binomial PDF. Our n is now 7, because she's only shooting 7 here. Her probability of success is still at 0.75. And we want to find the probability that she makes none of them. Okay, so I'm going to go ahead and plug in my calculator. It should do the same on yours. 7.75 and 0. And when I do, including the 1 minus part, I get 0.9999, and actually the next value is a 3, so that would round right to that value there. Okay. So what does that tell us? That means that essentially 99.99% of the time, she'll make her first free throw within the first 7. Okay, because she shoots 75%, so it would make sense that that would happen at such a high rate there. And now those were finding the exact probabilities. If we wanted to look to see the cumulative binomial probability, again, now we're looking for the probability that it's, she makes between 10 and 20 free throws, or something along those lines there. Okay, because that's something that's a little bit more applicable. Finding the probability of an exact value, well, if your sample size is small, sure, that might make sense. But as you get larger and larger, the probability of an individual event, as you kind of compare it to a continuous random variable, the probability of an individual event is going to be smaller and smaller as your sample size gets larger and larger. So this cumulative idea is going to give us a better understanding, really, of how likely events are to occur. So as an application, we frequently want to find the probability that a random variable takes a range of values, and the cumulative binomial probability is useful in these cases. On the calculator, it's just binomial CDF, emphasis there on the C for the cumulative, and we notice that we still have NP and X. But in this case, the X is telling us, oops, shouldn't have shown you that yet. The X is showing us that we have X or fewer successes. X or fewer successes. Now, what does that tell us? That means that if, let's just say the distribution were to look like this, sometimes they're left skewed, sometimes they're right skewed, sometimes they're more symmetric. But if we wanted to find the probability of, say, whatever, say that's 3 there, this is going to tell us the probability that it's 3 or fewer number of successes there. And we'll find the area always to the left of the binomial CDF. Just like the normal CDF, it's going to give us a range here. Okay. Now, if we were to look at, as we see here, the binomial distribution where we have the 12 observations and the probability of success is 0.75. If we wanted to find the probability of making 7 or fewer, okay, that's what this says here, probability of making 7 or fewer, well, same thing, NPX, and this is telling us that she's going to make 7 or fewer 15.76% of the time. Now, this is a more meaningful value here to consider. On the previous slide, we said the probability of making exactly 7 was about 10%. But what we see here is that she's going to make 7 or fewer 15.76% of the time. Now, that tells us that, again, she didn't necessarily choke in this case. That's going to happen from time to time, that she'll make 7 or fewer. In fact, it'll happen almost 16% of the time. Okay, but that last number 7 tells us that the probability of making 7 or 6 or 5 or 4 or 3 all the way down to 0. All right. This gives us a more formal definition of the CDF. This is given a random variable x. The cumulative distribution function of x calculates the sum of the probabilities. And this is the idea here, 0, 1, 2, all the way up to the value of x. All right, so again, telling us that it's a left-sided probability here. That is, it calculates the probability of obtaining at most x successes. All right, and that's important. We need to make sure that we're understanding that it's the left side. Now, what does that mean if we're looking for the probability that x is, say, greater than x? In other words, we have more than x successes. Well, all that means is we have to come in and do 1 minus the probability that x is less than x. Okay? That'll give us that probability. We have to find the complement of it. And as it says here at the bottom, it's very important to understand the difference between binomial CDF or binomial PDF, because obviously you're going to get the wrong answer if you do it the wrong way. Okay, so let's look at this example here. It says among employed women, 25% have never been married. 25% have never been married. Select 10 employed women at random. All right, so what do we have? We have 10 as our N, and we have our P of 0.25. And that's going to help us set up the rest of this problem here. It says, what's the probability that exactly 2? We can stop right there. Exactly 2. This is a PDF problem. What's the probability of exactly 2 of the 10 in your sample have never been married? So, since it says exactly 2, it's a binomial PDF problem. What's our N? Our N is 10, P is 0.25, and our X is 2. Binomial PDF, and PX, and we get 0.2816. Next question says, what's the probability that 2 or fewer? Key there, 2 or fewer. That means it could be 0, it could be 1, it could be 2. All right, exact same setup. The formula, or how we enter into the calculator, looks exactly the same, with the exception of, now we're talking about CDF, N is 10, P is 0.25, X is 2, and that's going to give us, again, the probability that's 0, 1, or 2. Notice the probability is going to be higher. All right, quite a bit higher in this case because, well, we're very close to the actual mean. All right, so that's the difference between using PDF versus CDF. All right, if I were you, I would stop the video at this point and I would try this problem on your own and then push play once you think you have the answer. At the beginning of the chapter, we talked about Gretchen, who's a 60% free throw shooter. In a season, she shoots an average of 75 free throws. That is our N. What's the probability that the following things happen? Okay, making exactly 50. Exactly 50. There's our X. And since it says exactly, we're doing a PDF here. So binomial PDF, our N is 75, our P is 0.6, and our X is 50. And we end up getting exactly 50, less than 5% of the time. Even though that value is close to the mean, since we're shooting 75, the probability of making exactly 50 or exactly 51 or exactly 49, the probabilities for all of them are going to be fairly low. But on the other hand, if we were to look at a problem like this where it says more than 50, now we're talking about a range of values for x, and now we can go ahead and say, well, it's going to be a higher probability here, clearly. All right. Now, this idea of more than 50, clearly that tells us that this is going to be a CDF problem. But we've already kind of clarified that the CDF command is a left-sided probability. And we kind of hinted to the idea that it's going to be, well, we have to find the 1 minus the probability there. But 1 minus what? All right, we're looking at the probability that x is greater than 50. So we're going to do 1 minus binomial CDF. Now here's what we have to be careful about. Not the N and not the P. Those make sense here. But it's this last number here. This last number is the key. Now we enter 50 here because what are we doing? We want greater than 50. So if I'm going to find greater than 50, well then I'm going to find in here the probability that it's 50 or fewer. 50 or fewer. And then I take that away from 1 to get the 0.0963. Okay, the 0.0963. Since we want greater than 50, now we're going to take the probability that's 50 or fewer, and then we're going to find that. And this last number here with the binomial CDF, especially when you're doing the 1 minus, that's going to take a little bit of practice before you truly are confident in what number you put there. But again, one more time, since we want the probability of it being more than 50, 50 is not included in the true solution. So when we take the complement, when we do the 1 minus binomial CDF, we include the 50 there because we don't want it in our true answer. Okay? The number 3 here says makes no more than 40. No more than 40. Does that mean 40 is okay? Yes, that means 40 is okay. In this case here, no more than means it could be 40, it could be 39, it could be all the way down to 0. This is a left-sided probability, so we don't need to do the complement. We can just come in and say x is less than or equal to 40. Binomial CDF and px, and again 40 is included, and that probability is 0.1446. Notice that writing the probability statement is essential. It is written in each one of these problems there, and that's something that is expected of you when you find your probabilities as well. Okay, a couple cautions here about this. Like I said before, calculator talk is not sufficient. Now, what does that mean? If you're doing, let's say you're doing binomial CDF, let's talk about the free throw example, 12.65. All right, if you're trying to do that, you can obviously have your calculator do that, but what the AP, and therefore what I would like as well, is I would like this written out. 12 choose 0, 0.6 to the 0, 0.4 to the 12, plus 12 choose 1, 0.6 to the first, 0.4 to the 11th, plus dot dot dot, all the way out to 12 choose 5 in this case, because that's what we're talking about there. So I'm going to run out of room. I'm going to turn it here for us. 0.6 to the 5th and 0.4 to the 7th. Okay? So that shows the understanding of the formula. And while I didn't have to write it out for all 5, I had to write it out 3 times. Annoying, tedious? Sure, it is. Okay? But that's what the AP is looking for, so that's what I'm looking for as well. But if you write it out in the formula, as I just did, and then just go right to using the calculator, and you can just give the answer from the calculator, that would be sufficient. You should write out the formula for each problem. They're on your formula sheet, so that's something that's a good, helpful hint for you there. But feel free to use your calculator for the calculations. Pretty much what I just said there. Okay. And for the cumulative, use plus, dot, 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 plus to show the first two and the last part of the formula, which is essentially what I just wrote out there above for you. Okay? So that's how to use the calculator for these binomial distributions. We'll practice this a lot in class tomorrow. And from here on out, okay, we'll go to the next level where we'll talk about finding the mean and the variance and standard deviation for these distributions. Have a good day, and I will see you guys in class tomorrow.